Dear students, as per request of some students, I am discussing today about the Newton's laws of motion. And first, I will discuss about the first law of motion. As we know that we will discuss three laws of Newton in this chapter, in this discussion, and this is first law of motion. And we know that each body continues to be in its state of rest or of uniform motion in a straight line unless compelled by some external force to act otherwise. Every body preserves in its state of rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed theorem. So if we discuss some example of first law of motion, a passenger sitting in a bus get a jerk when bus start or stops suddenly, and we can see that when a car take a turn suddenly, this the person sitting inside it's thrown outwards. Or we can see that a bullet fired on a glass window makes a clean hole through it, while a stone breaks the whole of it. The speed of bullet we know that is very high, and due to its large inertia, moment of inertia, it cuts a clean hole. The remaining glass remains in rest, while that portion become in the motion. So these are the example of Newton's first law of motion, that is also known as law of inertia. Everybody wants to remain in inertia, either it may be in motion or it may be in rest. This is the first law of motion. Now I will discuss about the second law of motion. Second law of motion means when we apply a force on a body, then the alteration of motion is ever proportional to the motive force impressed and is made in the direction of the right line in which that force is impressed. And if we see mathematically, then the rate of change of linear momentum is equal to that applied external force. Suppose this is a body and we apply a force on the body and it starts to move with velocity v. If mass of the body is m, then momentum should be m into v. So applied force, it should be rate of change of linear momentum. Or we can say it should be mass into acceleration. But when mass is constant. And P represents the mass into velocity. We can say that d upon dt. P means mass into velocity. When mass is constant, it becomes m dv upon dt, and dv upon dt is acceleration. So we can say it is equal to mass into acceleration. So this is second law of motion. And if we see that a force is applied on the body, then if force is applied in x dimension, then it should be equal to rate of change of linear momentum in x dimension, or we can say that max. It means we have to take the x component of acceleration. Similarly, we can say if we applied a force in y dimension, it should be may, and if applied force z dimension, then it should be dpz upon dt maz. So suppose if these are the forces in x, y, z dimension, then total force, it should be Ifx plus Jfy plus Kfj, where I, J, K are unit vectors. Now we will discuss about the third law of motion. Third law of motion, and it is also known as action reaction law. Action reaction law. So in case of two body problem of a system where total linear momentum remains constant, suppose it is constant, so differentiation of total linear momentum, it should be 0, and we can say dp1 upon dt plus dp2 upon dt is equal to 0, or we can say dp1 upon dt, it should be minus dp2 upon dt, and dp1 upon dt mean rate of change of linear momentum, that should be f1 minus f2. It means it shows equal and opposite force. It shows the action reaction force, that is known as Newton's third law. And in order to walk, we press the ground in backward direction with our foot. That is the one example of action Newton's third law. And when rubber ball is stuck against a wall, the ball bounce back due to the reaction of the ball. This is also an example of Newton's third law. And these are the point of noting that first law represents or defines force. First law defines force. Second law measures force. And third law gives the nature of force. These are the point of noting. Now we see some examples of the Newton's laws. So we can see the example that suppose this is a ground and a block of mass m is kept on the ground, then mass, due to mass, weight is acting in downward direction from the center of mass of the body, and a normal will act in upward direction opposite to the weight. This is in the case when a mass m is kept on the ground and it is not moving. This is case number 1. Case number 2, suppose there are two spheres. This is one sphere, and this is another sphere. This is sphere A and this is sphere B, and the walls are rigid. These walls are rigid and base is also rigid. So we can see, first we discuss about the sphere A. So this is, suppose this is sphere A. And suppose mass of sphere A is MA and mass of sphere B is MB. So mass will work on center it should be MAG, weight of the A sphere, and due to this plane, a normal is should work in this direction. Suppose this is normal N1, and due to this sphere B, this is sphere B, a normal should work in this direction, and we can take it NAB, normal from B to A, NAB. And this is the case exerted by B. And similarly, we can say the case which is exerted by A. Suppose this is sphere A. Now we are discussing this case we are now discussing. This is a sphere B, and now weight should work in this direction, MBG. Now normal should be from A to B. We can take it NBA, and we can represent it by NBA. And due to there is a wall, so normal should work N2. So here NAB and NBA are action-reaction pairs which follow the principle of Newton's third law. This is case number 2. And similarly, we can see the case number 3. In case number 3, suppose this is a plane inclined at 60 degree, and there is a body, and a force F1 is acted in this direction. 10 Newton is worked in this direction, and this 10 Newton is working normal to this plane. This is normal to the plane, and F2 is working in upward direction on the direction of plane, in upward direction. So in this case, now if we draw it separately, suppose this is inclined plane, 60 degree, and at this point, suppose this is a point P. At this point P, this is F1. This is F1, and this is 10 Newton. This angle, it should be 60 degree. This is F2, so this is F2 cos 60, 10, this is 60, so it should be 60 degree, and perpendicular, in perpendicular direction, it should be 30 degree, and it should be 60 degree. So 10 Newton in this direction becomes 10 cos 60, and in this direction it becomes 10 sin 60. And similarly for F2, it is F2 cos 60, and in this direction it becomes F2, we can write here F2 sin 60. So in x dimension, we can see in x direction, this is first force is F1 plus. Next, this is tan 60. It is also in x dimension. Tan 60 equal to these two forces F1 and tan 60 is balanced by F2 cos 60. F2 cos 60. This is in x dimension. Similarly, we can see in y dimension. In y dimension, this is a force in downward direction 10 Newton, and in y dimension first is 10 cos 60, second is F2 sin 60. This is F2 sin 60. This is also in y dimension, F2 sin 60 plus 10 cos 60 equal to 10. These two forces are balanced by 10 Newton in downward direction, this force. So this is third case by which we can balance the forces at a point, balance the forces of the component of the forces at a point. Next case is, suppose this is a string and this string is passed through a pulley and a weight of 10 kg. This is a weight of 10 kg and this pulley is in balance by the help of this rigid place. So we have to find magnitude of force exerted by string on this pulley. So if we see that this is a weight and weight should be worked in downward direction, this is mg, and in this case it should be 10 into 10 Newton, and same tension is worked in equal and opposite direction, so T should be 100 Newton. As the pulley is balanced by these two rigid plates AB, so equal and opposite tension should be worked and it should be also 100 Newton. And it means two forces are working on the balanced pulley at 90 degree. This is 90 degree. So resultant force is should be F equal to under root. Suppose this is T1 and this is T2. So we can write under root T1 square plus T2 square. As we know, the two forces are working perpendicular, then resultant force it should be F equal to under root FA square plus FB square. So resultant force it should be F equal to under root 100 square plus 100 square, or we can say 100 under root 2 Newton. This is the resultant force. Now we will discuss the next case. Suppose this is a plane surface and this is a body of mass m1, another body of mass m2. A force is applied on the body, and if we apply the force on m1 and m2 and both are in contact to each other. Now suppose total mass of the system is m1 plus m2, and if both mass is moving with the acceleration a, then we can consider that F equal to m1 plus m2 into a, or a equal to F upon m1 plus m2. Now if we find out the So find out the force which is transfer from M1 to M2. Suppose this is a body A and this is a body B, and we want to determine the contact force between A and B. We want to determine the contact force. This is contact surface, and we want to determine the contact force from A to B. So we know that in this system, in the whole system, sigma F, it should be equal to mass into acceleration. And if we see that this is M2 mass and An force is applied by M1 to M2, this is the direction of reaction, and due to this rigid surface, a reaction force, it should be work in upward direction, and M2G weight should work in downward direction. So sigma F should be R plus N minus M2G equal to M2A, and R is balanced by mg. R is equal to M2G, so R and M2G are cancelled out, so N becomes equal to M2A, and we know that A is M2, it should be M2. A should be F upon M1 plus M2. So this is the contact force which is working from M1 to M2 or body A to B. This is one case. And another case, in another case, suppose there is a mass of M1, a rope of M2, and another mass M3, and it should be balanced by a force. So we want to determine force. Second, net force on rope, and third, we want to determine the tension at, suppose this is middle point, at middle point of rope. Tension at middle point, this is middle point, tension at middle point of the rope. So we know that direction of F is in upward direction, and it should be balanced by M1 mass of first block plus M2 mass of rope and M3 mass of second block into G, M1 plus M2 plus M3 into G. This should be the value of force. And if we determine the force, net force on the rope, so we know that net force on the rope should be mass of the rope M2, and suppose A is the acceleration, then it should be the M2 into A. And third case, tension at the middle point, we know that third case, suppose T is the tension, this is middle point, so M2 by 2 mass of this part becomes M2 by 2, and mass of this block is M3, so below the middle point mass is M2 by 2 plus M3. So it should be in upward direction tension is T, and in downward direction mass is M3 plus M2 by 2 into G. So T minus M3 plus M2 by 2 into G it should be equal to m3 plus m2 by 2 into A, where A is the acceleration. So this should be the tension at the middle point of the rope. Suppose this middle point is P. Now next case, suppose this is a rigid place, a mass m1 and there is another mass m2. This is mass m1. So m2, due to m2, a force should be in this direction. We can say it n2, and due to m1, a normal should be in this direction. It should be n1. n1 should be in opposite direction, upper direction, and n2 should be in downward direction. And a weight should be worked in downward direction. So n1 minus n2, it should be m1 into g, as mass of the m2 has been included in normal, which is worked in downward direction, n2. So n1, n2 should be, suppose this is m2, this is n2, and this is m2g. So n1 minus m2g, it should be m1g. So dear students, in another video we will again discuss the Newton's law of motion with some other examples. Thank you very much.